Peter. Today we've got a talk by Matthew Wright on helium purification and how it's utilized here at the laboratory. Before we begin, I'd just like to remind you of two safety items. One is in case of a fire and the alarms go off, our mustering point is out through these doors, right through the central entrance, and then out the doors in the front of the building. There's a fire alarm pull station and extinguisher just outside the door here. Also, in the case of a tornado, we've seen a few of those recently, the exit's still the same through the bottom doors here, and then we have some interior offices and conference rooms here in the center area of the building for coverage. Okay, without any further ado, we'll go to Matt.
All right. Yeah, I figured that's the last time I'm going to hear that. Here's the purifier we're going to be talking about. We're going to talk about general purification, but I wanted to give you guys a picture of what this looks like in the general size of it. The top of the vacuum vessels come up about right here, and the top. I mean, I don't really have another really good picture of this. So this is some of the topics that we're going to talk about. I thought I'd start off giving you guys an idea of who I am. You guys already saw this slide, and you saw that one of those guys looking at the elephant right here, thinking he's looking at an ear, not an elephant, is operations guy. That's who I've become. Cryogenic operations, and that's my main focus, but I still get an opportunity to work on some of these engineering tasks. So a little bit about my background and why you might want to listen to me. I started working here at Jefferson Lab in 2000, and they gave me the purifier design to work around 2005. But after that, after I graduated with my BS degree, I started working on my master's degree. And in doing that, a lot of the work on that purifier would come to a screeching halt because I was more focused on getting my master's done, being a little overwhelmed by the new position, because prior to that I was a designer, and after that I turned into an engineer. So the fact that this took as long as it did to do is a crying shame, and I'm embarrassed by that, but it really doesn't take as long as this timeline shows. So we're here to talk about helium purification, and a lot of people get confused about what we're really purifying, and in fact, I put this dictionary.com definition up there because a lot of people say, well, what does it mean to purifier? But here at Jefferson Lab, we're only taking very small amounts of contamination now, and it's mostly, we're talking about air, a little bit of moisture, whatever's in the air, to remove the contamination from the helium. And like I said, it's a very small ppm level amount, parts per million. We'll get more into those details later in the slides. I also wanted to put up this little issue about oil. We purposely inject oil in part of our system into our compressors, or oil flood compressors. And we do that for many other reasons that I don't want to get into today. Oil is contamination, but if oil got into this purifier, there's no way to regenerate the purifier. So likewise, we're really not talking about oil either. We're talking strictly, mostly air. So why do we want to purify the helium? Pretty much, Brown already pointed it out. Any of the contamination in the air is going to end up in your cold box. The cold points of the box, the colder it gets, the more it wants to grab hold of any of the contamination. It freezes to the points. I show a little picture of a heat exchanger here. This gives you a representation. If you had a heat exchanger going from 300K to 400K, this is not how our refrigerators work, but just as a representation. 63K is the freezing point of, on a general basis, of the nitrogen. So if you ended up taking a slipstream of nitrogen, let's say 1 part per million, and flowing it through at like about 15 grams a second through this heat exchanger, over a year you would get about 4 liters. So that 4 liters built up in your heat exchanger, it's going to completely clog that heat exchanger and stop any flow that's going through there. So you can see that any contamination that we bring or get, even though it will affect moving parts, turbines, valves, how everything responds, you can also see that it will freeze out in your heat exchanger and completely block how your system's working. So when we talk about contamination, we have a closed loop, closed cycle system. And a lot of people say, okay, where's all the contamination come from? Well, we have to do, quite often we take part of our system and we'll basically turn it off. We have many different systems that are not online, they're not running. And if we don't leave them positive pressure with a small, just above atmospheric conditions, then what happens is that throughout the day of the temperature cycle, in a day, the gas inside gets warm because the sun's hitting it, or it's a hot day, and the gas expands, and it vents out any of the leaks or any holes, little small crevices. Remember, helium is the smallest molecule, so it has no problem escaping. And then at night, when it cools back down, the pressure in that pipe actually goes subatmospheric. So any of those little crevices of things are once again sucking in air, which is contamination to your piping. Now, it's very, very small, but if this is going through cycles and this is doing it for years, you'll end up with a lot of contamination. I point out that we have to go and do maintenance on some of our equipment. We have, oil-flooded compressors that are already mentioned, that if we do maintenance on that, we have to be very careful, because as soon as you open up to the system, the oil is very high, has a really high affinity to absorb the moisture out of the air. So it's going to suck the moisture right out of the air, right into these oily components. I also point out low temperatures. So if we're going to open up some of our cryogenic piping and it's still cold, then basically it's going to freeze out air. Just like you see this 80 Kelvin nitrogen line is freezing it out. If it's a 4 Kelvin, it's going to be even a larger ice ball. You're going to suck in, even if you have helium blowing in the opposite direction, like you're venting a small flow of helium. If you have a big enough pipe, and doesn't take that much, you're going to suck the moisture right back inside, and it's going to end up freezing out there. So when you get some sort of thermal cycle on the pipe or something, it releases the contamination and it ends up in the colder part of the cold boxes. So one of the other issues is that in our systems, in order to get the helium at the properties that we want to use it, we have these subatmospheric conditions. Now, for us, it's not as a serious of an issue for CHL. It's our large central helium liquefier, because we have other mitigations to try to alleviate any of the contamination being sucked in through there, mostly using guard vacuum, which is another discussion completely. So that's not as bad, but we do have heat exchangers for water, LN2, and hydrogen, and if those processes are higher pressure than the helium, the fluid flow always goes from the higher pressure to the lower pressure. But the big one here, and the most embarrassing for us, is we have to try to figure out how to stop losing so much helium, is how much helium we lose every day. And for any of you that have been behind CHL or over by CTF, you see these large white gas tanks. 300 liquid liters represents 2 of those. And in fact, we lose a little bit more than that right now, but this is the number that I had gone with originally. Now, if I'm replacing 300 liquid liters a day, and I don't purify the helium that's coming off the trailers, because we specify 5 parts per million, it doesn't take more than a year. It takes about a year, and we'll have 0.6 liquid liters, which still is a lot. So if you put 0.6 liquid liters in your heat exchanger, you'd end up having to shut it down and completely warm it up, and we're talking about weeks of time here. Now I put up how much we actually delivered on this particular day to just show you the order of magnitude. Normally the helium comes to us, doesn't have a lot of contamination in it. There is a trace amount of it. I have seen this number up to 5 and even slightly higher, but because we have our purifiers, we're protected and we clean the helium.
How do you measure that?
That is part of Jonathan Creel's talks. So you might want to go back. It's not in there to talk to him. But they have analyzers and arc cells that look and look at those things. And I haven't looked at too much. So how do we purify helium at at Jefferson Lab. Now there's a lot of different ways we could do this, but for the general, what we're going to be talking about as far as the purifier that I showed you the picture originally, this is basically the schematic.
300 liters liquid is an enormous amount. How can you lose that much?
That's my question. And we found that we lose a good bit of that at CHL and ESR, and at least half of it is my guesstimate from what I've looked at in the halls. It could be a lot of the designs, the original ways things are done. We lose it through a lot of relief valves. There are a lot of valves. There's a lot of connections. There's a lot of places.
Site-wide? Is that site-wide?
That's all the helium that the cryogenics group is responsible for. So, yeah, basically site-wide. So our purifier, it's real simple. Helium comes in the purifier, goes through our emulsive bed. I think I showed you the emulsive bed really represents trying to remove the moisture from it. The moisture doesn't get removed from the emulsive. Where does it end up? In your heat exchanger. So it's going to freeze out your heat exchanger, and we actually, I'm not showing it here, but we have an instrumentation to tell us the pressure differential across the heat exchanger. So if we start building up a lot of pressure, we know that we need to shut it down, warm it up, and switch over to the other purifier. Now all these the purifiers that I talk about, I always talk about a singular one, but all of our purifiers are dual. There's always two purifiers side by side, so as one of them's being regenerated, the other one's online. So it goes through the emulsive, through the heat exchanger. It gets down close to the liquid boiling point of the nitrogen, but because the heat exchanger is not perfect, we need to drop the temperature down a little bit. The liquid that's being boiled from the nitrogen, liquid nitrogen here, goes back through the heat exchanger and cools off whatever's coming down through here. And then that cold temperature goes down to the carbon bed and then back out, and the refrigeration is recaptured by the cooling the helium on the way in. What I don't show here is that we have attached copper straps and things to the carbon bed, but unlike some designs, the carbon bed is not inside the nitrogen boiler. So I put this little note down here for people because I find it very interesting that in a perfect world, we always look at our engineering calculations and we start there as what's the ideal. You don't need any LM2 on if this heat exchanger was perfect and there was no heat loss into the vacuum space. So basically the LM2 being on is just making up any of the losses of the inefficiency of your heat exchanger and the heat loss. Before I go too far, I wanted to talk about a couple different process options for purification. CHL, the purifier that I showed you a picture of and that we'll be talking more about, that is a slip flow purification. And it's mostly because I talked about the mitigation, the guard vacuum, and the cold compressors that we could talk more about in a different talk, but this is going to protect our systems a lot more than our subatmospheric room temperature vacuum pumps that we have at CTF. They are more prone to leaking. And so we do a slip flow to ensure that the quality of the helium stays clean, where at these other two facilities we have to be a lot more careful because of what's coming back to us from the equipment being used. Here I show you an example. This is a EDM screen. It's a capture what we look at when we do our operations. And right here we've added in well, when I say we, it's way before I got here, added in a purifier that, as you can see, there's the LN2 boiler, here's some heat exchangers. So it's very similar to what we already have as far as this other purifier. The big difference is there's no emulsive here. And I'll also point out that there are also 80K beds, as you see here, and there's also places that we have 20K beds. Now I know this is wordy. My wife wanted me to change this, but I put this up here so if you ever want to come back to it and really know, how it's a purifier. I'm mostly just pointing out emulsive removes the water, carbon removes the nitrogen, and a lot of people found it interesting that the carbon's made out of coconut shells. So it's a naturally occurring carbon that we use. So why do we go ahead and build a new purifier? Why not just take the ones that we have? and refurbish them. And so I pointed out a couple of reasons right here. One of the issues that I didn't put on here is that we use a lot more LN2, a lot more nitrogen during our regeneration process. The way these purifiers are, which is completely different than what we're doing, is that we'll end up wasting more of the resources. But we did. I wanted to point out that we got funded by Lindy. Our senior cryogenic staff went out there, and they're always looking for stuff that they find entertaining to spend their nights working on. And they suckered me into doing the same thing. Also, it helped me get my master's degree. And you can see that with this thing, the JLab gets a new purifier. You know, Lindy gets a purifier. I get my master's degree. There's very little cost to the JLab. This is a win-win situation for everybody. So this is some of the specifications for our new purifier and what we really started off with as a boundary conditions. And we really designed it for 40 grams a second, but we did check it for 60 grams a second. And I'll get more into the numbers and try to make it not as boring as I probably might do. But we're looking at 10 parts per million for water vapor, 10 parts per million for nitrogen, and we want it to last for a minimum of 4 weeks. As I showed you, that the nitrogen in the water, what we get in from our vendors is not that much. So our hopes is that it's going to last much longer than 4 weeks.
That's incoming helium, the 10 and 10, or is that what you're putting out?
So on the purifier process, and I don't show this, and maybe I should have, there's a whole auxiliary system, speaking strictly at CHL, where the pictures of the purifier and the purifier design. There's a separate compressor system that strictly adheres to that. So all the flow goes through those purifiers, through those recovery compressors, it goes to the purifier. And so that's any of the flow from the homes, any flow. We used to have a connection that went to CTF, but because of the construction that's been taken out. That's any of the flow coming from the Linax, anything that we're doing cleanup flows, anything that we want to have a dirty gas. So we say all dirty gas goes through this system, and then it gets put through the our purifier, and we're looking at 40 grams a second right now. Now in the future, if we ever wanted to expand out and expand the system, we wanted to have it so it had the capability to grow. If you wanted to get more compressors, bigger compressors, or do something like that. So a lot of the next statement, the design basis, I believe to me these are kind of common sense statements, but a lot of people, I'm going to try to put common sense into an easy to read format. Let me know if I don't do that. But we talked about our emulsive and our carbon bed already, so the temperatures that maintain. But when we regenerate it, we need to be able to raise the temperature because when you have the, let's say, take the carbon, it's at 80 Kelvin. And the contamination, I talked about, I showed you the slide a couple slides back. You know, you can see that this is an adsorption process, not an adsorption, but AD, absorption. The contamination actually adheres itself to the surface of the carbon. And so to be able to get that to release, you have to warm it up, and then we do these pump and backfill procedures, and I'll show you that in a couple of these slides. And in doing that, going through that adsorption process, the reason for using the carbon, and I showed you on another slide, is that it has so much surface area. So you want to go through this process, but once it's been saturated, once it's reached its limit, its ability to absorb the contamination, then you need to be able to shut it down, warm it up to these temperatures, and regenerate the process of the carbon and emulsive.
Back to the process requirements. So I didn't quite understand your answer. The 10 parts per million of water vapor and nitrogen, that's what the system is capable of removing without an issue?
Actually, it's capable of removing a lot more. But actually, minimum 0. But what we're looking at is like a standardized, what are the parameters? If I want this to, if I could send a lot more through here, 20, maybe 30 parts per million or even higher, but then the time frame, it'll affect the time frame. And I'll show you some quick calculations.
Yes, that's not what it's removing, that's the worst case you'll measure on the output. is 10.
No, I see your question now. No, this is the input. The output should be pretty much zero. You know, I don't think you get everything out, but now you're no longer talking the part per million level, you're talking much smaller. Does that answer your question? So we also had to be able to ship it, and we also had to fabricate it. And I know this is kind of an obvious statement there, but from the very first slide, you saw all the valves there, everything was in there. There had to be a process to come up with shipping. A lot of people say, okay, you built it here at JLab, you installed it, and you know, hopefully here soon in a couple of days we'll start, or a couple of weeks, months, we'll be able to run it. Why do I need to ship it? Well, we built most of it down in the shop. The guys then took it to a secondary location, put those components together, and then from those components picked the whole thing up and then moved it over into the location. So it needs to be able to take the rough beating around of moving it around in vehicles. Show you a little flow diagram there. That's just to say, ooh, wow. It's a lot more complicated than it is, but that's to show that there is plenty of instrumentation that goes with this. And if you can see the colors, which I can't when I look at the piece of paper, it shows you the primary flow condition. We'll go through that a little bit more later. So this is what I call the meat and potatoes of the project. This is our carbon bed. And for the carbon bed, these are some of the parameters that we stuck to. And I'm about to show you all those calculations. I'm going to try to run through them quick, not to bore too many people. But in order to figure out how much I can actually absorb, I had to figure out a couple of these, the absorbing capacity of the carbon. And I use this equation right here. And I could go through these equations a little bit more, but the point is that we found this excess absorption energy. And the reason to find it and converting it to these interesting units is because we get our little graph here, we get, and I gave you the reference for there, but basically this is what we're going to get from our vendors and people. And then I stole this from somebody else in our prior group as a quick little extrapolation of what that curve looks like. And I use that information after looking at the curve and getting that information to come up with how do I change moles, which is parts per million, this is the volumetric type thing, moles, into grams per second. And that's just basically, you're showing that, hey, these both have molecular weights, you take them, you get the molecular weight, you add the two of them together, then you divide the two of these, you find the percentage of your mass of nitrogen. So if I'm at 10 parts per million of nitrogen, and that's what this is really saying, and I'm at 40 grams a second, I'm going to come up with some sort of mass flow rate instead. So it's just a way to convert it from saying, hey, I have 10 parts per million to this is how many grams per second. Likewise, I take that mass flow rate of the nitrogen, I give it my time frame. How long do I want this to last before I get any breakthrough? And then I do a couple calculations and conversions, and I show you my mass of the carbon calculation right there because the units are kind of funny. And I come up with my mass of carbon. How much carbon do I really want? Well, from the vendor, they told us what the density is, and I come up with 100,000 centimeters cubed. 100,000 sounds like a big number, but in reality, it's only about 4 cubic feet of carbon. So we know how much we want. How do we come up with the size of the vessel itself? And so D is the diameter, L is the length, and we came up with this ratio, R is equal to L over D. And that ratio is kind of a guideline that we use. We say R really needs to be between 3 and 6, and I'll get into more about that in a couple of slides in here. And so we calculate using these formulas of, okay, what the standard sizes are we're going to come up with. And we notice that, hey, an R of 4 is really close to a 12-inch pipe ID. So we thought, well, maybe we'll give that a try. But before doing that, I need to make sure that with a downward flow purifier, different from having a process of blowing the helium up through the carbon because it might pulverize it, it might cause other problems, that my maximum velocity is in this order right here. So I calculate what my R is for my maximum velocity, and I come up with some numbers that are a lot smaller, decimal place difference than my maximum. So I said, okay, I'm good there. But in reality, using just some common sense here, I say if I have a really tall and skinny bed, then almost all the carbon is going to be used. But the problem is that the skinnier you make a piece of pipe with the same kind of mass flow and pressures that you're talking about going through here, then your velocities go up. Now our pressure is pretty high already. It's around 13 atmospheres is what we nominally run our purifiers at. And that is basically driven on the oil mitigation that we talked about. In this particular case, when we run our purifiers, you could run them at a lower pressure, but you would really, at that point, you would really have to be careful of your velocity, because as you lower the pressure, the velocity is going to go up for the same mass flow. Likewise, you can see this one. I don't know if you see the little red lines I have here. You know, basically the helium and contamination is just going to go straight through it, and all this carbon out here is pretty much not going to be used. So working in the cryo group, they don't let me miss turning any stone over, looking at anything. And even though these beds look like there's not going to be any pressure drop, it's not a big deal. They said, no, Matt, you have to do your equation, look at your pressure drop. I didn't put all the details of this up there because, quite frankly, it's pretty complicated to me. But we show that it's less than 0.1 psi for our 6-foot bed height. This is an interesting slide. It's hard to read unless you've seen it before. But imagine your contamination comes in this end of the bed. And I said the bed is vertical and the flow goes from top to bottom. But my little graph here, just imagine this is the top, this is the bottom, and this is the length of the bed. The contamination comes into the top. If you have 10 parts per million, the 10 parts per million is not going to be cleaned up in the top part of the carbon. It's going to take a little bit of penetration into this carbon bed for it to actually start to remove all the carbon. In my imagination, I believe it's going to probably look something like that, where at this point, okay, now it's clean. Now as this carbon gets saturated, this curve right here kind of walks its way down as the carbon all becomes saturated and the bed becomes less and less effective. So you get this breakthrough length. So what we do is we go ahead and add one pipe diameter size to the top of it, and then round it off for the nearest height. So there, from that, we basically have our 12-inch ID, or 12-inch pipe, carbon bed, 6-foot bed height, and our carbon bed is pretty much designed here except for the details. Our malt sieve, I'm not going to get too much into this, but it's pretty much the same process you go through to the carbon. The exception is that you have to be able to get whatever your absorption is from your vendor and find out what information they can give you from there. And they give you graphs to be able to do the same similar process. But you're looking at how many days is this malt sieve going to be for. Now, to simplify our whole process, we made the malt sieve bed and the carbon bed the same size. That way when we're shipping, we're not asking vendors to build this stuff. It's simpler on them. It's one part. Everything's similar. And the size that we're talking about is not out of the ordinary here. But when we calculate it out, it comes to 77 days. So it seems a little excessive. But in reality, we know some of our malt sieve beds may leak. And we actually, we decided when we're going to generate some of our purifiers here based on the differential pressure that is created across our heat exchanger. So we know the moisture is getting past the malt sieve, so we went ahead and made it the same size. We can be extra careful and not go to the letter of the calculation. This is my parameters that we sent off to our fabricator to build our heat exchanger. And I think they've talked a lot about the heat exchangers and the processes about those already. So I don't want to spend too much time on here. But I wanted to point out to you that the cold end of the heat exchanger It's very well known that the stream coming in and the stream coming back, there's going to be a differential temperature right there. And that's because we know that the heat exchanger is not perfect. And we design for it. It's part of the designs and how the process is done. So because we know that this has got a slightly higher temperature on the outlet here, then we go ahead and prepare ourselves by saying, okay, we have a nitrogen boiler in here, and I've already said that as the helium comes in here, it's a little warmer than the nitrogen, so it's going to boil any of that nitrogen off. And then as the helium enters the carbon bed and leaves. So one of the interesting things about this nitrogen boiler is that we wanted to build it here. And the reason we wanted to build it here is it's a little complicated. And we wanted to make sure that these tubes in here were built to our specification, and we were actually able to visually see that stuff and see how it's all built and be part of that process. In fact, they were able to wind up, and as you see a break here, there's actually 6 of these coils. We were actually able to build these things. So also this, there has to be plenty of height up here, so any of the liquid boiling here, or as the LN2 is being introduced into this area, it's not going to be 100% nitrogen. There's going to be a little bit of vapor with it. It gives it a place to separate out and then be able to move back to the heat exchanger. So this slide, like I said, talk a little bit about common sense. So how do you go about engineering? How do you go about doing a lot of these processes? So since I came here to Jefferson Lab, one of the things that they really beat into me is you've got to look at as many options as you can. And even an option that might not even make sense, it might sound like a completely idiotic option, might get you to thinking about some other idea. And so the real important thing is you take all these options right here, or these aren't options, these are, you come up with options for each one of these. I show you 7 different steps here. Come up with a minimum of 3 different options for those things, and then see how they all tie back in together. So you can see that you get 7 times 3 as a minimum for your options. It turns into a quite large matrix of question answers. Then once you get all your options worked out, and you think you have a good solution, you do an iterative step back. And so to me, that's really what engineering is. Whether you're using a model, you're using lifetime lessons learned, as we call in our operations group, no matter what you're using, you want to be able to iterate back to step 1 and look at everything. Now, I numbered these, and in reality, I don't think it really matters what order you go in. You could decide, hey, I really want to look at the flexibility in the piping first. You know, that might work for you. This is the order that works for me. This modes of operation, though, I feel really strong that you need to understand that one first. The modes of operation are saying, hey, I want this thing to run in this state, 40 grams a second. I want it to run 60 grams a second. Okay? Nothing really changes here. But what happens when your purifier has built up a level of contamination and it's time to regenerate it? Well, now you have to isolate it, you have to pump it down, you have to backfill it, you have to heat it. We talked about all those parameters. Well, how do you go about doing all that? If you don't know how you're going to do that, you don't know what process you're doing, you don't know what valves you need to use in there, you don't know the major components. And if you don't know that, you really don't know where you're going to put it, and you don't know how you're going to support it all because you don't even know what's there. So you really want to know what your modes of operation is. So let's go through our modes of operation. They're not that complicated. Gives me an opportunity to talk about a little bit more of my geometry or my organization here. It's one of my points that I make in my last slide here, right? So it all works together. And say that I walk up to this purifier and these valves are all of a sudden closed. But if these valves were all in the open position, what I would know is that purifier was online and flow was going through it. They're all the valves over here on the left-hand side. The left-right side wasn't determined. It was based on geometry, the easiest way we could step through all this. And it shows this is my normal online process. The next one is our helium conservation. So in reality, if the outlet's still clean, but we decide for some reason we want to regenerate the purifier anyway, what we want to do is save the 13 atmospheres of helium that's inside this bed and actually blow it down to atmospheric conditions before, so instead of wasting the helium and venting it, before pumping it down and venting the rest of the helium. We realized we wanted to do this from our friends at S&S who we helped design their purifier, and the lessons that they had learned and getting back to us. They said, hey, we lose a lot of helium during this process. What can you do to fix it? And so we went ahead and added the valve. Now it's all the way over here instead of in this column because it was an added on thing later, and we didn't take the effort to really put it inside of all this because it was just looked way too easy to put it right here as far as our geometry. I wish I would have taken time to do that, but it's something that we just didn't spend the time doing. So after we blow it down, that's this valve right here, so it's online. The next real step here is to open these valves and blow the whole purifier down. And that's all the rest of these valves are closed. And we're blowing them out. And notice that there's this little symbol right here, and that looks like a relief valve. Don't worry, it's not. It looks like one. The vendor calls it a relief valve, but in reality it's a regulator valve. Because you're taking 80 Kelvin gas, even though you blew it down to 1 atmosphere, and then you're heating it up to 150 degrees Fahrenheit, and you're blowing out. You're expanding that gas inside that pipe, and you have to have some place for it to go. So if we isolated the valve and used the system relief valve, somewhere there's one system relief valve and there's another one, then what would happen is that pressure that those relief valves go off at is much higher than your system pressure. So we already agreed that there was contamination in the bed. If there's contamination in there and you're higher than your system, and we have a rule in cryo, all valves leak, and you're basically leaking contaminated helium back into your process. So we take an extra step to make sure that that helium does not get elevated in pressure, and we can regulate it and mitigate any issue with backstream contamination. Once we've warmed it up, we blow it down the rest of the way. We blow our, this is a warm nitrogen helium, this is warm nitrogen blowing through the nitrogen bed, and it literally takes whatever liquid's in here and blows it out of it. Some of the designs that I've seen in the past, they don't have this feature, so it takes several days of heat and time to be able to get the nitrogen out of it before you can even start the regeneration process. So the key with some of these steps that I just showed you is that we should be able to do our regeneration process in 1 to 2 days with Purifier. So this just shows you our regeneration, shows you the path for the valves. And once again, I wanted to show you how to step through each one of these valves. This is the low pressure below down, and here are your vacuum valves. So you've gone through the whole process. Now, after you pump all the gas out of it, you need to put clean helium back in it. So you can do your pump and backfill with your heater on. And in this process, you notice that the valves don't fit up with the same stepping anymore. But in reality, this is part of the very first one because it's part of this valve right here. And so it does get a little messy there, but it should be pretty easy to follow. We have the same valve. The only difference between this process and the earlier processes is there's no heat on. And I've mentioned to you that during this process of the regeneration, there's no heat on in here. And I showed you a picture of the carbon bed already, way back there. And I meant to point out that this carbon bed that we're talking about inside the vacuum vessel has the heaters on it that Jonathan Creel talked about in his talk, that you have to have the right wires, you have to have the right system, or you'll end up burning it all up. There's another reason as you don't have any mass in the emulsive, or no helium in the emulsive, or no helium in the carbon, and this isn't a vacuum vessel, that it's really difficult to get the heat removed from there. So we leave the heaters off so we don't burn anything out. It's a precaution. backfill the regular operating system, and then you just cool it down, which is pretty much a reverse flow with your LN2 on. So that seemed very complicated to me, although to step through, and this seems very easy to me. Now, a lot of people might think just the opposite, but this is the same thing what you just looked at, but now it just shows you step by step and beside each other, and that's what I use to go through my layout and everything. My Purifier Layout, just wanted to point out here that these are some of these constraints that we talked about that we had to iterate. And these little tabs here are angles that are welded to the top head. Here's the heat exchanger, here's the nitrogen boiler, and here's the carbon bed. And these little two circles right here are 4-inch pipes that run from the very top of the head all the way down to the bottom. And at the top of the head, all this stuff is welded to it because we're using nature as heat rises and the cold sinks. So if the top is warm and down below is cold, we'll get less heat transfer from there. And I show you some pictures right here, showing you some more of the angles and the supports right here. And I show you over here, I don't know if you can see it too well, but this is a hairpin turn. So I purposely, for no other reason other than stress, to reduce the amount of stress that's being put into this leg, I put a little hairpin in here. You can use flex hoses, and we still happen to do so at the bottom here because it's a lot more difficult to find the hairpin. Came up with a couple options to push the hairpin turn at the bottom, but we found out that with a lot of extra pipe, a lot of extra welding, we figured that that's going to cause more complications, more chances for welds and things like that to go bad. Also wanted to point out that the height of this is around 12 feet. And later we'll talk a little bit about materials. In the bottom of this, it's not hard welded to the bottom. What we have is, you might be able to see it better here, is 2 pipes welded to the bottom plate, and the stainless steel 4-inch pipe, it actually fits inside of there, and it doesn't touch it because there's standoffs. There's a G10 sheet that is bolted to the bottom of that thing that actually keeps that steel from touching each other, so there's really very little heat transfer at the bottom. Talk a little bit about the requirements. You did do it to the B313. Some of the other calculations that we did, because when we did the LN2 boiler, we wanted to stick to the code. Same thing for calculation. Now, I used the hoop stress calculations because when I first started this, we didn't have the requirements of the B313. So I kept my little spreadsheet that I started. Now we have a much prettier, user-friendly that strictly uses the calculations from B313. But I thought I would throw something different at you guys so you can see the actual hoop stresses. And see that the level of stresses for the pressures that we're talking about, you know, I took a real high pressure here. I don't think it's any, you can see that. But this is our allowable stress, and you can see that the level of stress that we're talking about is very, very small for the internal stress. Now for the piping analysis, I used a program called K-Pipe, and in the do K-Pipe, what I did is I broke up each pipe spool into individual spools and gave it some assumptions and developed, okay, how's this one going to work? And we ran the programs, got some pretty colors and things. But the bottom line is, you kind of have to look at something like this, where it has 3 legs. Now, this is a relief valve up here. And you have a leg that's normally cold down here. And these are those flex hoses that I talked about. And we added them in there, not because there was any stress built up in this leg during normal operation, but we added this in here because there is a relief valve up here, and we had to assume the worst possible case. What happens if this relief valve goes off? So that we did all the calculations like that. Likewise, I also show this little guy right here because it, in a sense, is another hairpin turn. We could have come up, come over, and gone straight down, but when we did the analysis on that, we showed that it's a little bit higher on the stresses. By doing this, it does reduce the amount of stress in that leg.
When you selected your pipe stress analysis tool, what did you do to verify?
I spent a lot of time, probably more than I'm willing to say in front of everybody, doing hand calculations and verifying that my hand calculations for some basic counterleader type problems matched up with whatever the program was giving me. So I could do.
In your mind, you think you selected one that was adequate.
Yes. I think that.
You didn't take it on advertising value.
No, I don't take any of this stuff. They won't let me in the crowd group. they just want to say, how do you know? And they use this term giga at me or snake oil and tell me that, you know, what you're trying to come up with. So they made me go and do a lot of calculations.
You didn't use any marble mystery oil.
Well, okay, that's a new term for me. So, no, we don't. We really have to understand where it came from. I did do a couple of these things by hand using the Rourke's formulas in that back of the book there, and just some basic calculations.
You're good enough now to go on and generate your own code.
I could do that. I'm taking some classes on that. That's a lot of fun, but I realize that that is a career in itself. So not a lot of time spent here, but the heat exchanger is aluminum for the heat transfer properties. We do use a low carbon stainless steel, and I showed that some more G10 spacers. This is a little angle. It's welded to the side of the carbon vessel, and this is I didn't show you the threads on the rod here, but this is threaded rod. So there's very little to no contact from the threaded rod to the stainless steel angle. So we really reduced the amount of heat transfer using this hanging method. And this guy goes all the way to the top of the vessel, and as I said before, everything's welded at the top of the vacuum vessel, the head up there, and that's to try to keep the heat at the top and from everything propagating. And we also use this super insulating mylar. We also use the fiberglass around some of these areas where the heaters on. We did use a 3D modeler. Thought it was worthwhile saying something about it. And the process that we go through with generating that, because I was a designer when I started all this, so I was the one that modeled it all. But we based everything on the P&Is. So the P&Is, you find out what your modes of operations are. From the P&Is, you find out what your process diagram, what your valves, and how everything needs to go in. And once you have this, this is really the fundamental start of where your project should start. From there, we divided it into sections so we could do our fabrication, ease of fabrication, and how we were going to put all this stuff together. And then we divided everything up into sections. Instead of just taking one drawing, piling everything to a drawing, we broke it up into as many spools as we could. And that really helped when they did introduce the requirement to use D31.3. It was easy to really divide and conquer the whole project. So where are we now? We got all of our vacuum headers tied in, so we can pump it down. And as a matter of fact, we have pumped and backfilled the carbon bed and the emulsive bed, so they're clean. We flowed through them and sent that flow back to the existing recovery purifier system, because we don't want to send that into our clean system, to make sure that those beds are clean. They're actually flowing gas through them right now. And that's a recovery line that's tied in. Our LN2 and our GN2 have been tied in, and the LN2 has been tested. And we're ready to tie into our system. Of course, my understanding from our fabrication group is it's going to take about a week. That is to cut into it, weld on it, get everything cleaned back up, have because it's tying into an existing system, it's very difficult to do a pressure test. So what we're going to have to do is have somebody come out and RT the weld. And once we get all of that done, we'll be up and running. So I'm running a little fast today. But there's my conclusion. If you have your surveys that you're supposed to fill out and turn back in, I wanted to help you guys out, give you the answers for you. So if you don't know what a purifier is, here's the answer. If the helium is not purified, continuous operation would not be possible. You know that. So you can go through and read that. Do I have any questions?
How did you get on to B31?
I was told to go to B31.3.
You didn't know about it before?
Oh, I knew about it, and we actually designed a lot of this. We started the design with the intent of the code in mind, so it wasn't that difficult of a transition to make. It was more paperwork than it was anything else, coming back and proving the calculations.
Who told you to use it?
Yep, management. Our friends in management.
It's a laboratory standard. It's also a nationally recognized standard. So it's one that you have to follow within the DOE guidelines.
And it's a good code to follow. I mean, there's a lot of good points in there.
So every 4 weeks, you replace your purifier, correct?
Well,
Is that what you?
what I'm saying is that if I had that level of contamination, I would have to regenerate the purifier. We don't have, there's 2 purifiers. How do we go back to the first slide? As you can see, that's the purifier right there. In fact, there's 2 purifiers. So you can see it briefly, there's a shadow. That's one vacuum vessel. This is the other vacuum vessel. Over here behind this electronics are the emulsive beds. Give you an idea that the emulsive beds aren't really that big. Those are 12-inch diameter. And this side of the valve rack goes to this purifier, and this side of the valve rack goes to that purifier, these gauges, henceforth. And so what we do is when we decide whether it's from a high DP across our heat exchanger, or whether we're getting some sort of indication of a contamination breakthrough through the beds, or maybe we decide just we want to put it on a schedule. It looks good for, if it looks good after 3 months, let's just go ahead and regenerate it anyway. We might come up with some sort of policy like that. We haven't done that yet because we haven't really commissioned it. So once we get to that point where we want to regenerate it, the other one's already standby, cold, and ready to be turned on. You just basically open these valves over here. That one's now online, and close these valves over here and start the regeneration process that we went through this modes of operation. And then you have the 2 of them regenerated, and it's cold, standby, and ready to go into service at any point.
Matt, what is the regeneration time currently on the current ones at CHL? How often do you have to regenerate this?
The current one takes about a week, and
I'm sorry, how often?
once a month. We have it set up on a schedule, more or less than anything. We do occasionally see a high DP across the heat exchangers, and then we'll just go ahead and regenerate it at that point. But we've kind of found that sticking within a week is a good time. When we do regenerate it, it takes about a week because there's no way to blow the nitrogen out. And the way to heat these beds is by taking heating nitrogen, warm nitrogen already, and heating it up a little warmer and flowing it over the outside of the bed. So you cannot flow the nitrogen inside the carbon bed because that's contamination, but you can flow it on the outside and try to get that heat exchanged that way. Does that answer your question?
My curiosity here, so is it a safe assumption that there's a number of companies that make these kinds of things? Is that a true statement? That's not my question. I just want to know if that's true, then I'll ask the rest of them.
I don't know, is the answer to that question. Maybe Ralph?
The answer is that Lindy approached us and gave us funding to develop this because there really isn't any commercial large purifiers. We have some associated with very small refrigerators that will just clean up the refrigerator and some small streams, but not as a sort of like dedicated system to clean up helium so we can reuse it.
So what I was going to ask, if it would have been true, I was just curious if you guys had any, do you have to do any looking into patents to make sure that you're not building something that some other companies got passed on, that sort of thing?
Well, I think Lindy funded everything, and the
Well,
purpose
that's-
behind funding it is so they could have the design. And I think we pretty much, it's their design, right?
What design?
Our design, but they kind of own it.
It's an
Right?
old technology. It's been used for a long time, more than 30 years. Even if many patents exist and expire on that.
And we have different purifiers, that's what I was trying to show at one point. We have 3 operating cryogenic plants here. CHL is our large one. We have the ESR, that, not too small. And then CTF is a real small one. And each one of those has a different way of setting up their purification system. Anybody else?
The purification process is continuous. Just
is I don't know if I can go through the slide fast enough, is the purifier that we're replacing inside of here, there's a lot of stuff that needs to be refurbished on it, and that's really the only thing that's wrong with it is it needs to be refurbished. And something that I didn't point out here, I should have, is that the needs refurbishment, part of that is that the carbon inside and the emulsive inside need to be removed and replaced, because over time, any oil migration that might be in the system ends up in that carbon, and you can't get that back out through the regeneration process. And so there's no way to remove the carbon from this vessel. You'd have to cut into the vacuum vessel, cut into the carbon bed, remove it, patch everything up, which I'm not sure how you would do welding on something with carbon on the other side, and go from there. On the design that I just showed you, there are ports on the top of it, and on most of it there's one on the bottom, but I didn't put one on the carbon bed because it's inside the vacuum vessel. But we've proven that you can take a vacuum hose, put it down to the port, suck all the carbon out, and just replenish it with new carbon. It goes through a regeneration process, and you're back online. It looks like little pellets of, crushed up rock type thing, but it's lightweight, it's black, it's really dirty. It's coconut.
Get it on your finger and you've got it all over your place.
Yeah, it's something if you want to play a practical joke on your friends, get it on their face and all over the place. I'm sorry.
Is there an issue with when you introduce pressure pulverizing?
Right. So part of the
Avoid that, I guess.
I tried to show that, and I did not point it out. I should have. In my modes of operation, when you're blowing these beds down, blowing it down isn't as bad. But notice that this valve right here is very small. And so when you're taking the gas out, you're using a small valve. It's going to take longer. But we put a small valve in there for people like me that might forget the procedure, and you just open the valve up full, and that should be good. And then likewise, when you go to, after you've done the regeneration, you have no gas in this vessel. And it's the carbon sitting in there, essentially in a vacuum. And you go to open up your valve, and because there's no pressure, the velocity is a lot higher in that helium. And that helium will pulverize the stuff inside the bed. And so what we're trying to do to alleviate that is that in our backfill process, there's a metering valve that's added to it, and that's this real small valve here. So what we tried to do is say we're going to use a real small valve, we're going to make it a metering valve, so we just have to crack it open. And so then you're only slowly introducing the gas into it, the velocity should be kept down, and there should be very little pulverizing of the carbon. Does that answer your question? Absolutely. We have run into problems in the past during certain situations where, we're scrambling to get one set of purifiers regenerated because the other ones aren't, the other ones are getting ready to be taken offline. And so the way the purifiers are built right now, because it takes so long because of the process, it makes it a lot more difficult. With this one, it should make it a lot easier, a lot less scurrying around. And if we really need to get this thing done very quickly, we'd probably work around the clock and have it done in 24 hours. Well, right now, we have the existing purifiers online. So they're going to stay online when we put these online and then commission these, and once these are fully commissioned, then we'll take the other ones off. Somebody over here?
I see the multiple use ball valves. Have you found a ball valve that doesn't leak?
Well, in fact, they have a couple of ball valves that they prefer, the technicians that work with them. And we prefer them a lot more than these ball valves. And it's one of the things that I wish I would have known, because I started working on this project. We actually bought all these parts before I even got into operations. And once I got into operations and they started telling me about this, I was like, uh-oh, they're not going to be too happy with me when they see all these ball valves. In fact, that they weren't. So it's always a challenge to try to keep the leaks out when we're trying to do the regeneration process, because it gives you a false indication of how clean the decks will be if you have any leaks in those valves. So far, these have been pretty good for us. Very, very small. Anybody else? Robert?
You had a step in there for helium conservation, taking that gas back. How significant are helium saving for that over time? So?
Well, as I showed, I mean, the amount of helium that we're saving compared to the amount that we're losing is a small amount, especially if we do get to this every 3 months that we regenerated. But we should be taking any steps that we possibly can because it's becoming a more and more important issue. Helium is becoming more expensive. I have a fear that, me working on helium refrigerators might not have a job here in another 20 or 30 years. So we need to get better about that.